Brandon, the space and physics editor at Live Science, has spent more than 2 decades covering complex topics in science and astronomy, with his work appearing in The Washington Post, Reader's Digest, CBS.com, and platforms like the Richard Dawkins Foundation website. His extensive experience in science communication allows him to explain cutting-edge discoveries in ways that engage both experts and general readers. With a bachelor's degree in creative writing from the University of Arizona and minors in journalism and media arts, Brandon combines rigorous reporting with compelling narrative, making highly technical subjects accessible. Recently, his focus has been on 3I/Atlas, an interstellar comet currently passing through our solar system, a rare event that has captivated astronomers, space agencies, and the general public alike, offering a glimpse into materials and processes beyond our solar system. The European Space Agency, ESA, is utilizing spacecraft originally designed for Mars and Jupiter missions to observe 3I/Atlas as it travels through the inner solar system. This strategic deployment demonstrates the ingenuity of scientists in maximizing the scientific return from missions already in operation. First detected in July 2025 by the ATLAS Asteroid Terrestrial Impact Last Alert System telescope in Chile, the comet quickly drew the attention of astronomers worldwide due to its unusual trajectory. Unlike typical comets that orbit the Sun in predictable paths, 3I/Atlas follows a hyperbolic route, indicating that it originated outside our solar system and is making a one-time passage through. Traveling at roughly 130,000 miles per hour, 219,000 kilometers per hour, it is only the third confirmed interstellar object, following the discoveries of Oumuamua in 2017 and 2I/Borisov in 2019, making it an extraordinarily rare phenomenon. The comet's interstellar origin was identified not only by its unusual trajectory, but also by its unusually high velocity, far exceeding that of solar system comets. This makes 3I/Atlas a unique scientific opportunity, a visitor from another star system, carrying primordial material that may predate the formation of our Sun. Observing such an object allows scientists to compare its composition with comets formed within our solar system, potentially revealing the chemical diversity of planetary systems across the galaxy. However, observing the comet from Earth presents significant challenges. Astronomers estimate that it will remain visible to ground-based telescopes only until September 2025, after which its proximity to the Sun will make observations difficult, and eventually, it will move behind the Sun from Earth's perspective. To overcome these observational limitations, ESA and NASA are leveraging spacecraft already positioned throughout the solar system. Between October 1st and 7th, ESA's Mars orbiters, Mars Express and ExoMars Trace Gas Orbiter, will observe the comet as it passes near Mars. The closest approach between the comet and these spacecraft is projected to be around 30 million kilometers on October 3rd, providing a relatively close perspective for capturing high-resolution images and measuring gas and dust emissions. These observations will help scientists analyze the comet's activity, including the behavior of its nucleus, the composition of its coma, and the structure of its tail. NASA's Psyche mission, en route to the metal-rich asteroid 16 Psyche, will also have the opportunity to observe 3I/Atlas, adding complementary data to the dataset gathered by ESA's orbiters. Even though Psyche's instruments were primarily designed for asteroid study, they can capture images and spectroscopic data that help track the comet's path and physical characteristics. The most critical observations will occur around perihelion, the point when the comet reaches its closest approach to the Sun. ESA's Jupiter Icy Moons Explorer JUICE mission is scheduled to observe 3I/Atlas from November 2nd through November 25th, just after perihelion. At this stage, solar radiation triggers the comet's most active phase. As the Sun heats the comet's ices, they vaporize and form a luminous halo, or coma, surrounding the nucleus, while a long tail streams behind. Observing the comet during this phase allows scientists to analyze its chemical composition in detail, identifying water ice, carbon-based molecules, silicates, and other compounds. This provides a chemical fingerprint that could indicate how 3I/Atlas's materials compare to comets that formed within our own solar system, potentially revealing differences in the formation environments of different star systems. T. Marshall Eubanks, chief scientist at Space Initiatives Incorporated, emphasized that JUICE is uniquely positioned to capture critical data during perihelion, offering a vantage point that cannot be matched by Earth-based observatories or spacecraft orbiting Mars. While other missions, such as Mars Reconnaissance Orbiter EMBRO, TION-11, and HOPE can gather valuable information, JUICE's instruments and location make its observations particularly significant. Capturing the comet's behavior during this peak activity phase provides essential insights into its composition, surface activity, and structural integrity. Understanding how interstellar comets respond to the sun's energy helps scientists model the physical and chemical evolution of such objects as they journey through the solar system. Studying 3I/Atlas also sheds light on the broader nature of interstellar objects. Unlike comets confined to our solar system, which experience regular cycles of heating and cooling, interstellar comets travel vast distances through empty space, exposed to cosmic radiation and extreme temperatures over millions of years. Observing 3I/Atlas can reveal how such objects preserve volatile ices and other primordial materials, offering clues about the resilience and long-term evolution of interstellar bodies. Comparing its composition with solar system comets may also help determine whether the processes that produce comets are broadly similar across the galaxy or whether each planetary system follows unique formation pathways. The observation campaign also highlights the adaptability of modern space exploration. ESA and NASA missions, originally designed for planetary study, are being repurposed to monitor a rare interstellar visitor, showcasing the versatility of spacecraft and instruments. Coordinated observations from multiple platforms allow for cross-verification of data, providing a more complete understanding than any single spacecraft could achieve alone. This approach maximizes the scientific return from missions already in operation and exemplifies the importance of international collaboration in studying rare cosmic events. Beyond its scientific significance, 3I/Atlas has captured public imagination, much like previous interstellar visitors. Its discovery by ground-based telescopes, followed by coordinated observations from spacecraft throughout the solar system, illustrates the synergy between professional astronomers, space agencies, and the wider public. Events like this inspire interest in STEM education, foster curiosity about the universe, and highlight the excitement of real-time space exploration. Science editors like Brandon play a critical role in translating these complex observations into accessible narratives, allowing the public to follow the comet's journey and understand the groundbreaking science behind it. As 3I/Atlas continues through the solar system, scientists are meticulously tracking its position, velocity, and activity to gather as much data as possible before it becomes too distant to observe. Even after it exits direct view, the data collected by ESA, NASA, and other observatories will provide a lasting resource for future comparative studies, modeling interstellar object dynamics and preparing for encounters with similar visitors. Every measurement, from spectroscopic signatures of gas and dust to the comet's rotational dynamics, adds to our understanding of interstellar comets and their role in the broader cosmos. In summary, 3I/Atlas represents a rare convergence of opportunity, technology, and scientific curiosity. Its discovery and observation by multiple spacecraft provide an unprecedented window into material from beyond our solar system, offering insights into chemical processes, planetary formation, and the physical evolution of interstellar objects. The collaborative efforts of scientists, engineers, and science communicators like Brandon ensure that these discoveries are meticulously documented and widely shared, fostering public engagement and expanding our knowledge of the universe. As 3I/Atlas races through the solar system at extraordinary speeds, it serves as a reminder of the dynamic, interconnected nature of space and humanity's enduring desire to explore and understand the cosmos. The observations collected during this fleeting encounter will likely shape our understanding of interstellar objects for years to come, offering a foundation for future exploration and inspiring curiosity about the mysteries that lie beyond the familiar orbits of our home planets.